I have a couple things to talk about. So first is the exam. It's not graded yet. Sorry, it's not done yet. Um, Second is let's see, practice problems. Um, I got to get those up soon. That's a top priority for me. So you'll have all the practice problems uh, by the end of Thursday, and you'll have all the solutions by the end of Friday. Okay, and then you have like a week with all the problems and solutions.
What are it's on is the finals on everything?
No, no, the final. Okay, so the final it's not a final. It's just a fourth exam.
Okay.
And what? It's not optional exactly. I mean, I suppose it is, but it really hurts your grade if you don't do it. Um, so it's just going to cover this friction stuff that we've been doing. We're going to finish today. And then it's going to cover what we're doing today and Thursday, which is virtual work. Just an introduction to virtual work. Okay. So I'll get practice problems up for all that stuff and solutions up. And the exam will also be graded by the end of the day Friday, I guess now. Um, and the exam is 8 a.m. on Thursday, the 16th.
How long
Okay.
do you expect it's going to take?
It's going to be 80, it's the same as the other ones.
Okay.
So I expect most people to be done in an hour. That's about what I shoot for. Some people to take an hour and a half. Um, and then there seems to always be one person who
So we have
who stays the whole time. I don't know. So, I mean, I guess okay. So when this has happened before, like, uh, I had a physics test last year, and after like 2.5 hours, how long do you have? 2.5 hours, 3 hours for the, and after 2.5 hours, I was just kind of like, really, like you've been alone in this room now for an hour. Can we just like, do you feel like you're really like, do you feel like you're really developing your understanding of this stuff as you wait here? I know exactly. Yeah, like she's gonna just derive like the rederive Newton's second law or something. I don't know.
At 11, do we still need to show up at 8?
Yeah, so yeah, please show up at
You can't
8.
show up at 10?
Yeah, please don't do that. Um,
Okay. I just want to be company for the last person.
yeah. Um, any other questions about the exam? So just like the other exams, to study for it, you got to be comfortable with the practice problems. That's why I need to get those practice problems up soon, and I will do that. But for now, the uh, the practice problems are going to be very much like the example problems that I gave last class and the ones I'm giving this class. Okay, so you can get a sense for what kind of, like, it would do you good getting ready to just go through these examples. Um, you can sort of think of them as more practice problems. Okay, any other questions about the exam? Yeah, so all the friction stuff, so square threaded screws, um, the two different kinds of bearing friction. Um, and that's all, right? That's all, I think. Um, and then just general, friction sliding like a block on an incline, which is uh, really the same thing that you're doing with the square threaded screws. Um, and then this virtual work that I'm going to talk about today. And the virtual work stuff, since I'm just presenting it for the first time today, Um, it's going to be a very basic introduction to that stuff, um, but it comes up all over the place, and I'll talk about that more. What?
The multiple choice part of the exam.
You could think of it that way, multiple choice, but there's infinitely many choices, and they're not given.
That's worse than Steele's multiple choice.
Does he have A through G, and then
No, it's
H is
multiple
like
choice.
A, C, D, and H?
Multiple choice, but you have to show all your work.
Oh yeah, right. Right. So it's just sort of like it's a problem, but at the end you can check your work against one of his answers, kind of.
Yeah, right. And no partial credit.
Oh really? Oh. Um, he consistently comes up with creative ways to scare the bejesus out of people. Okay. Any other questions about the test? All right, so let's talk about the problem set for a second. So the problem set, if you look at this thing from the side, you have a shape like this, that the long axis inserts into this hole, okay? And the way to think of this is as if you have, so this goes in here, and think of there being another side that I didn't draw, that inserts over here. Okay, so this whole thing fits together. And so you don't have to worry about, just given what I drew, and you apply this downward force here, right? Then you'd have to worry about this moment. So you might be thinking you insert this in here, and now you're pushing this end down. So what's happening as this end rotates down and this end rotates up. You don't have to worry about that. Okay. By the way, like, what's the equivalent if? So say I left this end off. How would I show that? How would I show the same thing, that you don't have to worry about this? I guess the way that I would do that, maybe what I should have written is, so this is going to produce a moment about, say, this point here, right? Calculate that moment. It's this length times this force, and that moment direction is going to be, as a vector, it's going to be out of the page, right? It's going to be counterclockwise. So you would say that the metal here that's omitted from this drawing provides a couple equal and opposite, okay, to hold it up. And then you don't have to worry about that. So I suppose maybe I should have, do you happen to remember what this force magnitude is? Okay, so 10,000. Oh, and I didn't give a length. I guess that was so whatever this length is, make m equal to 10,000 L, and then you don't have to worry about that rotation. But it's the same thing as this happening two places, and there being a 10,000 Newton force split between the two of them. Okay. So what you have here is you have this force, you also have this force, right? The force being applied axially is causing end-bearing friction, right? This collar here presses up against this wall, okay? And so you have to deal with that collar bearing, that end bearing pressure. And then this 10,000 Newton force causes just regular axial friction, like journal bearing friction between this point and this point, okay? So you're just dealing with the two of those at once, okay? So that's all this question is, and once you follow what's going on, once you can make sense out of the geometry, it's not much calculating, you know. It's just making sense out of what's happening that takes a little time, I think. Any other questions about that? Okay. Well, before I go on to virtual work, I'm going to just do two examples. This is the kind of thing that you're going to have to do in the practice problems. So it's the kind of thing that you're going to have to do on the exam. And basically, those derivations that I did, I'm not going to want you, like I'm going to give you simple questions, but those aren't meant to be just treated as formulas to use. I want you to do similar derivations. You can plug in any numbers that I give you, okay? But so the way that I'm going to solve this sort of long way, that's how I want you to solve these problems, because I think it just sort of keeps it stuck in your head, the ideas that this is based on, and that's what's important. It doesn't matter if you happen to know what page the formula is on for journal bearing friction. So, okay. So for the first example, this is journal bearing friction. And it's important to remember with all of this stuff, the applications, the number of applications for this is limited by the fact that this is all dry friction. Okay, so none of this represents friction in lubricated joints. Okay, so what? My car is an application, but most people's car is not a good application of that. So there are some, but basically, like you wouldn't want to set something up that's going to be moving continuously this way, because it's causing damage the whole time it's rotating. All right, so let's say that we have and I suppose the most realistic applications might be the static friction questions about this, like when is motion going to start when you have this friction applied? You know, that kind of thing. Like, what's the maximum moment you can apply before this thing starts to turn? Because you don't want these things turning, you know. Okay, so here are your two bearings. And they're connected to wheels. The axle's connected to wheels. And these two bearings are loaded 5,000 newtons each. So that represents, you know, the weight coming down from a vehicle or something. And we're going to ignore the rolling resistance. We haven't talked about that. But there's a friction. There's also, you know, resistance acting between the ground and the wheel. How do you know that? How do you know that exists? Because remove the axle and just roll this wheel along a flat surface, and it doesn't roll forever. So you know, even in a vacuum, it doesn't roll forever. So you know there's friction between the wheel and the ground too, but we're not concerned with that. Okay, so the coefficient of kinetic friction, we'll say, is 0.2. And we'll say the radius of the axle is 5 centimeters. And we want to determine the torque that has to be applied to the axle. In this case, the axle is connected to the wheels. So, you know, this torque can be applied to any part of that solid thing. To keep the axle rotating with a constant angular velocity. Okay, so we'll start with a free body diagram of the axle. And what loads are acting on the axle? There's a 5,000 Newton force coming down. There's this moment that we're trying to calculate. And I didn't specify a direction. I guess let's give this a positive orientation, and the sign will come out for itself. So if okay, this is the radius of the axle. What other loads are acting? Okay, so there's a friction and a normal force. I think the way to think about this, to me, the way that makes sense to me, is there's only one other force acting. Okay, there's only one other thing causing a force, right? This is the force caused by the weight acting down. This is the axle pushing down. This is... Oh yeah, you know what's funny about this? This is actually a little bit... This one's actually a little bit different. So in this one, in order for this to balance, we have a normal force coming up from the ground, right? And that's connected to the axle, right? So really here we have our force of 5,000 newtons acting this way, okay? We know that there's going to be this external torque M applied to keep this rotating. the only other thing applying a load to this axle is the bearing, right? Which means that it has to balance that 5,000 Newton force if this is going to be rolling along a horizontal surface, right? And since that's the only other load applied, it can't act right through the center, or this moment would have nothing balancing it, okay? So the 5,000 Newton force acting from the axle has to be, let's see, if this external moment is making it counterclockwise, this 5,000 Newton force has to be offset this way to counteract it. Okay, who's with me, first of all, on the why I switched turned this upside down? Okay, so the force that's directly applied to the axle is coming from the wheels and the axle are all one piece, okay? So there's this upward 5,000 Newton force that's applied from the ground to the wheel, to the wheel, to the metal next to it, the metal next to it, next to the metal next to it, until we get to our cross section. And then we have this upward force of 5,000 newtons. The bearing is what's pushing down in this case. Okay? So, okay, and if the moment is acting this way, the external moment, that means that this is the direction of rotation, right? So this 5,000 Newton force acting down, produced by the axle, can be broken up into a normal force and a friction force, right? The normal force is this. The friction force has to counteract the direction of motion. So there's the friction force. And this friction force has to be equal to 0.2 times the normal, right? And now we can use this relationship to figure out what this angle is. Because we know if this is the angle, we have, well, you can think of this as the tangent of that angle is equal to opposite over adjacent 0.2n over n, so 0.2, okay? So if we make a triangle that looks like that, we can make the opposite 0.2, the adjacent 1, then the length of the hypotenuse is square root of 1 squared plus 0.2 squared, so square root of 1.04, and that gives you, let's see, could someone calculate that? I guess I don't know. What? 1.02. Okay. Okay. I guess we also can, if you take you could also calculate that angle, but there's no need to here. So once we have this triangle, what are we trying to calculate? What we're trying to calculate, so we can get this applied moment, is we're trying to calculate this moment arm. I'll call that rho. Okay? Because we know we have this 5,000 Newton force, right, acting down. If we can figure out what this rho is, we just multiply those two together, and it gives the applied torque that has to. It gives what this applied torque has to be counteracting. Who's with me? Okay. Should I start this over? Or are people following this all right? Yep.
So we're imagining that like the whole rest of that circle around that axle isn't having any friction. We're just worried about that one point that's got the pressure.
This point here.
Yeah.
Yeah, that's right. That's right, exactly. So yeah, we're taking the whole, so the same way that with the square threaded screws, we boiled down all of that surface area of contact into just a single block sliding along an incline. Here we're boiling down any contact that's happening into this one location, okay? And we know that if we're gonna do that, this location has to be to this side of the center because it has to be equal and opposite to the applied torque, okay? We know there has to be an applied torque from experience, okay? So in order to calculate the torque created by this offset axle force, we need to know what that force is. We know that from Newton's second law. We have a 5,000 Newton force coming up from the ground, so this has to be 5,000 Newtons. The only other thing we need is the moment arm rho. Okay? And to calculate this moment arm rho, notice that this angle of this triangle is equal to this angle. Okay? So, this rho is equal to the radius of the axle times the sine of that angle. We know R, that's given, is 0.05 meters. The sine of this angle we can get without even calculating that angle, although you could use an inverse tangent to get that in the first place. Sine is opposite over adjacent, so yeah, opposite over hypotenuse. So we got 0.2 over 1.02. And so you get a moment arm of 0.00981 is what I got, meters. So that's the torque produced by the contact with the bearing. And the only torques acting on the axle are that torque we just calculated and this external applied torque. which is equal and opposite direction. So m is 0.00981. No. Multiply those out. M is 5,000 times the moment arm. And you get 49.05 Newton meters. What?
No.
Okay, so this is the torque you have to apply to keep this rotating. How would you do this problem if I asked, this is just sitting here, what's the torque that has to, or what's the maximum torque, say, that can be applied to this axle before this starts turning? You just have to use static friction, but the problem would be exactly the same. Okay. And so this is the level of work that I want to see on this, the level of the derivation. Just I want to see a free body diagram with the normal force, the friction force drawn in there. You're going to have to do some kind of trigonometry. It's fine with me if you just use the inverse tangent and get that angle and then work from the angle. But for the moment arm, yeah. That number is with my, I think I got like, I just had it 1.0198 instead of 1.02, and that's how I got slightly different answers. Okay, any questions about that? All right. That was my warm-up. This one's going to be clear. So now let's do an example of end-bearing friction. So say that you have this cylindrical shape in contact with the ground. You have a 15,000 Newton force acting down on it, so pushing these two surfaces together. Say the coefficient of static friction between these two surfaces is 0.5. And the radius of this cylinder is 0.1 meters. And the question is, what's the maximum torque that you can apply before this starts to turn? And for these problems, I want to see you go through the integral derivation. Okay, they're always going to be cylindrical shapes, so it's not going to it's going to be very similar each time. But I just want you to get used to using this way of thinking about this problem. So in cross section, we want to figure out for each infinitesimal ring around the center, we want to figure out the increment of torque that friction is producing. Okay. So that's the moment due to friction of this infinitesimal ring. Okay. So to do this, we're going to figure out the pressure over this whole surface. Okay. Then we're going to figure out the increment of normal force in this infinitesimal ring. From that, we're going to figure out the increment of the friction force in the infinitesimal ring. Then we're going to integrate that. Or I guess, sorry, before we integrate, we're going to figure out the increment of torque in the infinitesimal ring. And that's going to be d force of friction times the distance from the center to that infinitesimal ring. And then finally, we're going to integrate. Okay, to get the total moment due to friction. All right, so the first step is to figure out the pressure. The pressure is just the total normal force divided by the area. So we have 15,000 newtons divided by the area of that whole cross section. So pi r squared. And you get 477,465 pascals. And now we're going to use this fact. So this is a force per area, right? We're going to come up with an expression for the incremental area of this ring. So if we're looking at this ring, its area is the circumference times the thickness, okay? The thickness is our increment dr. This is the distance r. So we have 2 pi r dr for the increment in area. The increment in normal force then is equal to the pressure times the increment in area. So 477,465 times 2 pi times RDR, and you get 3.000 times 10 to the 6th times RDR. Anyone have any questions about that step? Okay, so given that normal force, so this is the increment in normal force applied just in that infinitesimal ring. So what's the total friction force applied in that infinitesimal ring? It's going to be that normal force times the coefficient. So the increment in friction force is equal to 0.5 times the increment in the normal. So we get 1.5 times 10 to the 6th RDR. Now the increment in the moment is R times the increment in the friction force. So that's 1.5 times 10 to the 6th R squared dr. Step 5, now we just integrate this. We have everything expressed in terms of the variable r. So we're going to integrate 1.5 times 10 to the 6th r squared dr. And what are the boundaries of the integral? Yep, 0 to big R. So that's 1.5 times 10 to the 6th times r to the 3rd over 3, evaluated from 0 to 0.1. So that's 5 times e to the 5 times 0.1 to the 3rd. And you get 500 Newton meters. Anyone have any questions about that one? Okay. So the last topic we're going to go into is virtual work. And we're not going to get this to a point in this class where this really becomes a good alternative to the methods that we've already done. But we will talk about it enough that you can sort of see the potential for it, I think. I'm bringing this up because this is an introduction to energy methods. Um, and one of the benefits of energy methods is that instead of solving a system of vector equations, you solve a system of scalar equations. And you know, worrying about vector directions and stuff can be a little tedious, but that's not really the main benefit of this. So I'll talk about what the main benefit is of energy methods. So energy methods come up in sort of the two branches that come out of statics. One is mechanics of materials, like deform, that a lot of you are taking next semester. In mechanics of materials, this energy method gives you a new formulation of equilibrium. And in some cases, it's easier to solve. On my dissertation project, the problems that I solved, I did all using an energy method. And maybe the most practical application of an energy method that anyone who goes into like a mechanical branch of engineering ends up dealing with is finite element analysis. So the equations that go into finite elements, really the main numerical method for solving mechanics problems, are all formulated in terms of energy. Okay. And so in order to understand finite elements, you have to understand the idea of these energy methods. And in dynamics, the other big branch that comes out of statics comes Lagrangian dynamics. And Lagrangian dynamics is really useful for linkages, dynamics of linkages. Linkages are just collections of rigid bodies that meet at joints, like our structures, except they're moving, and you have to calculate the dynamic. You have to calculate acceleration and velocities. And it also lends itself really nicely to computer programs. So it's the approach to dynamics that is used in dynamic software packages. So it's good for programming. Okay, so here is really the general benefit. In certain problems, energy methods let you avoid solving for quantities you don't care about. And here's a example of how that doesn't happen in the methods that we've been talking about, Newtonian methods. So say that you want to analyze a structure like this. And we've dealt with structures like this a million times. There's a 1,000 Newton force acting down. This distance is 1 meter. All these angles are the same. And say that what you want to find is just the horizontal reaction force, you know, the horizontal component of the reaction at B. Okay, so I'm not gonna go through this problem, but let's just think about what would be entailed. So first, we draw a free body diagram of the whole body. We have the 1,000 there. We have the components of the force FB here, the components of FA, right? We have 4 unknowns then. We only get 3 equations from this free body diagram. So we have to move on to one of the members. So say you isolate this one then. You have the 1,000 Newton force. You have the force, the reaction force between the 2 members, F12. You still have FA. Now you can solve it, okay? But in the process, you had to solve for all these things that you didn't want in the first place, right? You had to also solve for F12, FA, and the component FBY. And all we wanted was FBX, okay? And I'll do this example after I present a method for the virtual work. And we'll see that we end up being able to bypass all that other stuff we don't want and just focus on the one variable that we're interested in, okay? So in some cases, and this is one of those cases, you get what you want without taking as much computing power, you know, in a, like, that's the benefit in a computer program. Okay. So in order to introduce this method, first think of work done on a particle. If you have a force F applied while a particle goes from this point A to B, right? And I'll call this the R vector. Then the work done by F on the particle over that path is work equals F dotted with R, right? So if the force and the motion are perpendicular, then there's no work done, right? Um, it's similar if we just look at some incremental change in location, okay? We're just dealing with an increment dr instead of a vector r. So incremental change in position. So say we're going from now a point A to a nearby point, A prime, under the influence of this force F. Now this increment is dr. And we'll say that the increment of work done by F over the path dr is du. So we're going to use u instead of w. Keep your eye on the ball, though. Is the force dotted with the increment dr. Okay. And if you wanted to, so then if this force was changing as this path moved around, you could integrate this, solve this as a line integral, right? And that's a way to calculate work if you don't have a constant value of the force. Remember doing that? Did you do that in 1121? Oh, okay, okay. So, well, you can do that. It's not that hard. So what if you're not dealing with a particle, you're dealing with a collection of particles? Because that's what we care about, right? I mean, we care about mostly particles collected into rigid bodies. So what about a collection of particles? Well, oh, sorry. Skip that for a second. So I want to say one more thing about this back here. So this is kind of the key to this idea, this chapter. So what if that particle is in equilibrium? Okay. Well, if it's in equilibrium, the total force acting on the particle has to add up to 0, right? That's what we've been doing in statics this whole time, right? So the sum of the force vectors is equal to 0, right? So any increment in work through any infinitesimal displacement you move this particle, okay? If you look at this formula, 0 dotted with dr is 0, right? So the total increment in work has to be equal to 0, okay? And what that tells us is that when something's in equilibrium, in some sense, like the energy that object has is at an extremum. Okay, it's either at a maximum or a minimum, right? You make little changes in, so you can picture this whole, like, you have this big energy landscape, and anywhere you bump it, you're moving horizontally. Okay, you're not changing the energy no matter where in this landscape you move the object. Okay, so now for collections of objects, collections of particles, since that's true for one particle, it has to be true that you add up the increments in energy for all the different particles, and they're equal to 0, right? For any set of increments dr, if the collection is in equilibrium. That wouldn't be too useful except for a couple of cases where the incremental work is equal to 0, okay? And that's going to let us simplify this a lot. So this wouldn't be too useful except for 3 simplifications. The first one is consider the work done by forces between particles that are part of the same rigid body. So these two things are fixed relative to each other, right? This overall body can be accelerating around, it can be rotating, okay? But the distance between these can't change, right? And the net force between these two particles has to be in line between the two particles. And they can't change distance, right? You can think of that as like a definition of a rigid body. So, if one particle gets an increment in work du, the other gets negative du, right? If one moves to the left, the other one also moves to the left, right? The forces are equal and opposite. You know what I mean? So when you take that dot product, those those works are equal and opposite. So the long and the short of it is you can neglect any du produced as an internal load in a rigid body, okay? So if you're looking at a system of particles, and so you're looking at this system of particles that's organized into a rigid body, you're still going to have to worry about the increments in work done by external forces, okay? But you're not going to have to worry about any of the stuff that's happening inside because they come in pairs that are equal and opposite, and they add to zero, okay? You know what I mean? Like that. So if you're dealing with, so we said up here that for a collection of particles, for something to be in equilibrium, all of these virtual works have to add up to zero, right? So think of like the virtual work done on this pen right now, okay? So it's not really a pen, but so there's one force coming from my hand, right? And there's a million forces between the things in the rigid body, okay? So it would be really bad to have to add all those up. But this says all of those produce work in equal and opposite pairs, and so we can forget about that and only worry about the work done by my hand as we move this thing around in these little infinitesimal motions, okay? So that's really good. That's really good. That's the most important of these three. The second simplification has to do with the forces applied at frictionless pins. Okay, so if you have a linkage, a structure, and there's a pin here, we know that Newton's third law says if you have a force vector here, then over here you have a vector negative F, right? And these two forces are both acting on a particle at the same spot, the middle, right? And that middle, that one thing, obviously has the same dr no matter where you're moving this, right? It's the same point. And so one gives you a positive work of 10, the other one gives you a negative work of 10. And so you can throw those out, you know? Anytime you come up with this matched pair of equal and opposite works, you can throw that out and not worry about it, okay? So so not only can you neglect all forces between parts of a rigid body, forces internal to a single rigid body, but you can neglect forces between rigid bodies at frictionless pins. And that's really the thing that makes this so useful for linkages, is that we're not going to have to, like in a Newtonian method, we have to calculate all these internal forces. With this energy method, we can just throw all that internal stuff away, Okay, it's not good if you want to calculate those internal things, but and the third simplification is inextensible cables. And the reasoning is the same. If you have, say you have these two objects connected by a cable, since the cable is inextensible, if this moves in the direction of its cable tension force, then this one has to move opposite the direction of its cable tension force, and those have to be equal in magnitude. So, the effect of these three is if you have a structure that's built up as a collection of these three elements, that's rigid bodies, pin joints, and inextensible cables, then you only have to calculate changes, increments in work due to external forces. Okay, forces external to the structure. So that's the benefit. And so next time I'll talk about how to treat couples, and then we'll get into a method for using this for actual problems, and we'll do that example that I put up there but didn't solve before. Any questions about any of this?